Hi, my name is dr. Ahmath. In this video lecture, we are going to continue our discussions about parametric curves. In particular, we are going to discuss how we can apply tools of calculus, namely differentiation and integration, over the parametric curves. Well, first of all, define what is the parametric curve or what is a parametric equation over the curve. So parametric curves often are very useful if you would like to trace some paths. For example, if you would like to go to the mountains and this curve describes your path, and if you would like to be interested to find the length of this path within some interval of the time, then that's what you have to use. So you have to use calculus over the parametric curves. So let's define why we can't really use the calculus tools for the ordinary functions over this curve. I mean, the main reason is because this curve is not a function. So let's consider an example with a circle. Circle is the set of points which are equidistant from the center of a circle, right? So the distance between any point from the center on the circle from the center is going to be the same, which we call as the radius of the circle. Well, that's the basis how we are going to derive the equation of the circle. So I'm going to choose any point on the circle with arbitrary any coordinates, so x and y. And I know that by the definition, the distance between this point and the origin should be equal to the radius. And if you remember, in order to find the distance between the 2 points, what I have to do is I need to subtract the corresponding coordinates, x minus 0 in this case, in the square, plus y minus 0 in the square, and this should be equal to the radius in the square. So, well, if you have got a unit circle with a radius 1, namely, then you're going to obtain this kind of formula for the distance. And that's going to be nothing else as an equation of the circle. X squared plus y squared is equal to the 1. And the problem is, it's not a function, so that is why we can't really use the techniques of calculus which we have learned so far for the functions with the single variables to this curve. Well, it fails to be function because of so-called vertical line test. So one of the easy ways to check whether you've got a function or not, you can just make a vertical line, and if at any point of your curve that any vertical line is going to cross this more than once, then that's not going to be a function. So here for this circle, so you're going to have many this kind of vertical lines, but just one vertical line is going to pass your curve more than once is enough to do not call this curve as a function. So that is why this curve, a circle, the equation of a circle, fails to be a function, and we can't really use the techniques of the calculus for the single variable functions anymore. So the idea would be to define the equation of a circle differently. So is it possible to define x and y, two coordinates of any point over the circle, on the circle, just using one number, which we are going to call as a parameter? So if I would just look to this points, I would say that, hey, probably it is possible. Then I would just call the x coordinates as x is equal some function of this parameter, and y coordinate of any point over the circle is going to be another function of the parameter t. The only thing is we have to figure out what is going to be the parameter. Well, the good thing is, or the very good idea to define this parameter would be this angle. So I'm just going to find the line between this point and the origin. Then I'm just going to find the angle between this line from this horizontal line, x line. Okay, so that's going to be the angle, and this angle is going to define me the points. Okay, so I can find the x and y coordinates of these points by just making this kind of triangle. So this is going to be the right triangle, and if you know the angle and if you know the radius of a circle, you can always find y and x. So you can see here that you can define this point using this value of the t, but if you slightly change the value of the t, you're going to be able to define another point. You see, so just using one number, namely the angle, you can define the two numbers, the coordinates of any point on the circle. Well, if you know the trigonometric ratios, you can figure out what is going to be the y and x. Because so the radius of this circle, of this unit circle, is equal to 1, and we know by the definition that sine is the ratio of the opposite side, right? Opposite side to the hypotenuse, right? In this case, the sine of t is going to be equal to the y over 1, and the cosine of t is going to be the ratio between the adjacent side to the hypotenuse. So the sine of t, it's y over 1, and cosine of t is equal to the x over 1. So you can see here that y over 1 is simply y, and x over 1 is simply x. So you've got the parametric curve, parametric equations of this circle. So x is going to be equal to the cosine of t, sine is y is equal to the sine of t, where t is going to change from 0 to the 2 pi, right? So t can take the values from 0 to the 2 pi, because one-time revolution of the angle around the point, around the center of the circle, makes 2 pi of an angle. And you can see here that by just making one-time revolution of this red line, you're going to be able to obtain any point on the circle. So that's the beautiful equation of a circle, and you're going to see in a moment that we can apply really all of the techniques of the calculus over these equations in order to find a different physical phenomenon. So one thing I want is to generalize this equation for any circle with any radius, with any center, with center at any point. So if the radius would be different, not 1, but for example 2, then if you remember the ratios for the sine, right? Do you remember? So let's assume that the radius is going to be any point r, or any length r. If you remember that the sine of t is the adjacent side divided to the radius, right? So in our case it was simply 1, so that we just skipped this, but in general it's going to be like this. And if you find a y from here, y is going to be equal to the radius times the sine of t. And the same was the cosine of t, so the cosine of t is equal to the x divided to the radius. And if you find the x from here, it's going to be the r times the cosine of t. So if you would like to generalize this parametric equations for any circle with any radius, you have to just multiply cosine and sine to the radius of a circle. So now if you would like to change the center of the circle, it is also going to be easy. So what you want is you would like to define the parametric curve, parametric equation of a circle with any radius. So now we know how to do this. We just need to scale cosine and sine to the radius. And with the center at any point with the coordinates h and k, you have to simply add this h to the x and k to the y, where h and k are going to be the coordinates of the center of a circle. So in general, the equation of parametric equation of any circle with the radius r and at the center with the coordinates h and k is going to be in this form. Well, for example, if I would say what is going to be the okay, so let's say now you are given the equation with the center at the point 2 and 3, right? So 2 and 3. So this is the coordinates of the center, 2 and 3. And radius is equal to the 2. So you can just substitute everything into this equation, to the general equation, to find a particular equation of this particular circle. What I want is I would like to find the equation of the tangent line to the circle at this point, 2 plus square root of 3 and 4. So well, first of all, what I have to do is I need to find the value of the parameter t, which gives me this coordinates of a circle of this point. So in order to do this, I'm just going to substitute this point, the coordinates of this point, to any of this equation. So let's do this for the x. So 2 plus square root of 3, right, is equal to the 2 plus 2 times the cosine of t. So what is the value of the t, which gives you the left-hand side? So in order to do this, I'm just going to eliminate this 2 and 2. And what you're going to have here is simply square root of 3 over 2, right, is equal to the cosine of t. And you can guess that the t is going to be equal to the 30 degrees, right, or simply pi over 6. Well, if you substitute the pi over 6 to here, so what you get is 3 plus 2 times the sine of pi over 6, and we know that the sine of pi over 6 is equal to, say, 1 over 2. It's going to be 3 plus 1, which is 4, which is the y-coordinate of this point. Well, t is equal to the pi over 6 for this equation, parametric equation of the circle, is going to give you the coordinates of this particular point. Well, now what we want is we would like to draw a tangent line to the circle at this point and find its equation. Well, in order to find the equation of the tangent line, you need to know the two parameters of the tangent lines of any line, which is essentially the slope of the line and the y-intercept. And if you remember, the slope of the line is nothing else as the derivative of the y with respect to the x. So the k is going to be equal to the y prime, which is dy over dx. Well, the problem is we don't have just y is equal to the f of x form of the function. We are going to have separate curves for the y and x, so that is why I'm going to write this down in the form of dy over dt divided to the dx over dt. So this is what we can do. We can find the derivative of the y with respect to the t, and we can find the derivative of the x with respect to the t. So let's find the derivative of the x with respect to the t. That's going to be equal to, so this 2 here is going to be simply cancelled because it is a constant, and the derivative of the rest of the terms of the x with respect to the t, it's going to be equal to the minus 2 times to the sine of t. Well, derivative of the y with respect to the t is going to be the similar result. So this 3 is going to be cancelled out because it is just a constant, and the derivative of the rest of the terms is going to be equal to the 2 times to the cosine of t. And now we have to just substitute this into the formula of the slope. So the k, the slope of this curve, is going to be equal to 2 times to the cosine of t divided to the minus 2 times to the sine of t. And we have to evaluate the slope at the t is equal to the pi over 6, right? So this is the formula for the slope at any point of the circle. You can find the slope at any point by just changing the value of the t. So the t is your parameter. You can just play with this t in order to change the points on the circle, in order to change the slope of this tangent line, and so on. So just using one point k or t parameter, you can change all of the things. So now let's just substitute the pi over 6 to here. It's going to be 2 and 2 are going to be cancelled. It's going to be square root of 3 over 2 divided to the minus 1 over 2. Well, that's going to be minus square root of 3. That's going to be the value for the slope of this tangent line. And now in order to find the y-intercept, I just need to substitute the coordinates of this point into the equation of the tangent line, which I have found so far. And let's do this. So the slope of the tangent line is equal to the minus square root of 3. The equation of the tangent line is going to be y is equal to the square root of 3 with the minus x plus b. And if you substitute, for example, this point into this equation, it should be fulfilled. It should work. So I'm just going to substitute the y coordinates. It's going to be 2 plus, I think it was vice versa, right? So the y coordinate is 4, and the x coordinate is minus square root of 3 times the 2 plus square root of 3. So there is a typo, because if you remember, the point has x coordinates to be 2 plus square root of 3 and y coordinate to be equal to 4 plus the b, and from here I have to find a b. So the 4 is equal to minus 2 square root of 3 minus 3 plus the b, and the b is going to be equal to 7 plus 2 square root of 3. Well, that's going to be the y-intercept. So if you would like to find the equation of the tangent line, then it is going to be y is equal to the minus square root of 3 of x plus the b, which is 7 plus 2 square root of 3. Well, that's going to be the equation of the tangent line to the circle with this particular parametric equation at the point t is equal to the pi over 6, or at the point with the coordinates 2 plus square root of 3 and 4. Well, let's go further. So it appears we can apply other techniques, other applications of the derivatives into the parametric curves. Well, what I want is now I would like to find the length of the curve, which is defined using the parametric equation. Obviously, the length also is going to be defined by some interval for the parameter, by some interval for the angle. So let's say I've got this point. When I choose the parameter to be equal to the t0, then I'm just going to go over the circle, over this curve, along this curve until the parameter t1, and I would like to find its length. So the same as you are going through some passes and mountains, you would like to find its length, right? So you are going alongside this curve in some interval for your parameter. So in this case, it might be the length of the pass in some interval of the time. For our case, for the circle, it is going to be the length of the curve of the circle with respect to an interval of some angle. So it appears we're going to use the similar formula which we have used to find arc lengths. It is going to be equal to square root of derivative of the x with respect to the t in the square plus derivative of the y with respect to the t in the square. Then we have to integrate this in this interval of the parameter t. So let's just use this formula to find the circumference of a circle with a radius 1. So we know that it's going to be equal to the t pi, right? So I've got the point at the t is equal to the 0. So the angle of this curve is on the x-axis, so that is why the angle is going to be equal to the 0. So I would like to just go around the circle or alongside the circle for the angle t pi, 360 degrees. So the t0 is going to be equal to the 0 and t1 is going to be equal to 2 pi, and I would like to find its length. So if the radius, or let's do this with any radius, so we know that the equation of a circle with the radius r at the center was the coordinate 0 and 0, it's going to be equal to the r times the cosine, sine, cosine of t, and y is going to be equal to the r times sine of t. Well, we have to find the derivatives and substitute this into the curve. Derivative of the x with respect to the t is going to be equal to the minus r times to the sine of t, and derivative of the y with respect to the t is going to be equal to the r times the cosine of t. And if I substitute the dx and dt and dt into this equation, what I'm going to get is the length, the arc length, or the circumference of a circle with the radius r is going to be integration from 0 to the 2 pi of the square root of the square of this term, right, which is simply r squared times the sine square of t, plus the square root of this term, which is the r squared times the cosine square of t dt. Well, you can see here that r squared are the common term for both of the terms. I can take out the r squared from both of the terms and take out even from the square root. And what is going to be left inside is simply sine squared plus cosine squared, which is equal to the 1, right? So I'm just going to immediately write this down, the integration from 0 to the 2 pi of the r dt, because we know that sine squared plus cosine squared is equal to the 1 always for any angle. So the integration of this, the unpi derivative, it's going to be r times the t from 0 to the 2 pi, and using the Newton-Leibniz formula, we can substitute the 2 pi and 0. Here it is going to be equal to the 2 pi times the r, because if you substitute the 0 instead of t, it's going to be simply equal to the 0. So we can find the lengths of the curves, which are defined using the parametric equations, using this formula, which is basically the same formula which we have used to find the arc lengths. So now I would like to go even further. I would like to find the surface areas. So for example, if your curve is given using the parametric equation, and if you obtain some surface by just rotating this curve around some axis or around some line, then you can find the surface area of this curve using this formula. So in particular, if you would like to find the surface area of a sphere, what you have to do is you need to take a circle, or half a circle, I would say, right? So what is going to be the equation of a half a circle? Parametric equation of a half a circle was the radius r and at the center 0, 0. It is the same. So the only thing is you have to just define the area, the interval for the parameter. It's going to be x is equal to radius times the cosine of t, and y is equal to the r times the sine of t, where the t is going to change from 0 until pi, right? Because you're going to set the points, for example here, and you're going to rotate this until pi. So this is the pi angle, right? Not until 2 pi. Then if you rotate this half a circle around the x-axis, you're going to obtain a sphere. What I want is, I would like to find the surface area of a sphere. Okay, so with the radius r. So let's do this together. So I am just going to use the equation which we have just derived and put this into here. So if you remember, we've already calculated that this term, after we've taken the derivatives, is equal simply to the r, to the radius, right? So I'm just going to use the previous results to just substitute this. If you missed that, so just go a couple of minutes before on this video to find how we derived that this is equal to the r. So the x is equal to the r times the cosine of t. Y is equal to the r times the sine of t. Then I'm just going to substitute them into here. Well, the surface area is going to be the integration with respect to the t, right? Do you remember the t is your angle? So how to obtain this half a circle, or this half a circle? In order to do this, you have to rotate this line around this 0, right? For the angle pi, from 0 to the pi, from 0 to the pi. Then you're going to rotate this half a circle around the x-axis in order to obtain the sphere. So I'm just going to substitute this. It's going to be 2 pi times t. Y here is equal to the r times the sine of t. Multiply this term, all of this term from the square root is simply going to be equal to the r, surprisingly, and multiply it to the dt. We have to integrate this with respect to the dt. So 2 pi r in the square are the constants. I can take them out from the integration even. It's going to be 2 pi r in the square. Then integration from 0 to the pi of the sine of t dt. Well, the antiderivative of the sine is going to be equal to the minus cosine of t, and we have to substitute the 0 and pi to this. Well, if you substitute first of all, so let's do this together. 2 pi r, it's going to be minus cosine of pi, right? Minus cosine of 0. Well, cosine of pi is equal to the minus 1, so in total this term is going to be equal to the 1. Cosine of 0 is equal to the 1, so in total this term is also going to be equal to the 1, with the 2 minuses in front of cosine of 0, right? So that's why it's going to be simply 1 plus 1, which is 2, so at the end you're going to have simply 4 pi r in the square. This is r in the square, this is r in the square, which is the formula which we knew from the school, right? And we can easily get the surface area of the object, which is obtained by revolution of some curve around some axis or the line using this parametric curves, or the calculus over the parametric curves. So today we've learned that some curves are not possible to define using the functions. We're going to define them using the parametric curves, where x and y coordinates of any point alongside this curve is going to be defined using 2 functions, and the input, the argument of those functions, is going to be called as the parameter. So by just changing one number parameter, you can find any coordinates, 2 numbers of points along this curve. We've learned how to find the lengths of this curve within some interval of the parameter, and also we've learned about how to find the surface areas when we are going to rotate this curve around some line or axis and obtain some surfaces.